Welcome back to AI Paper Podcasts. Today we're going deep on this one. Scaling test time compute without verification, or RL, is suboptimal. It's a paper that really kind of shakes things up in terms of how we think about making AI more powerful.
Yeah, definitely. This paper really digs into some interesting questions. It's by Amrith Settler, Nived Rajarman, Sergey Levine, and Avril Kumar. And they're really tackling a very important problem, How do we get the absolute most out of an AI's thinking process, especially as we're hitting these limits with data?
You know what I think is really interesting is how they frame that thinking process as test time compute. So we're not just talking about the compute used during training, right? It's the computation used when the AI is actually generating a response.
Exactly. And what's really cool is that they're making this argument that simply scaling up that test time compute without a system for verification, specifically using techniques like reinforcement learning with the verifier, it's actually way less effective than we might intuitively think.
Okay, so I think before we go any further, let's make sure everyone's on the same page here. Can you break down what they actually mean by verification and why it's so crucial in this context?
Absolutely. So imagine you have an AI that's trying to, let's say, solve a math problem. A verifier is essentially like another AI that checks the first AI's work. And it gives it feedback. A thumbs up if it's right, a thumbs down if it's wrong, and maybe even some hints about where it went astray.
So it's almost like having a teacher or a more experienced peer kind of looking over the AI's shoulder and guiding it towards the right answer.
Exactly. And what these authors found is that this feedback loop is super crucial for actually making the most of increased test time compute. Without it, the AI might kind of wander down these inefficient paths or get stuck in these local optimas, even if it eventually, stumbles upon a correct solution.
Now, for our viewers in the first minute, let's give them like a super concise summary of what this paper is all about. What are the big, key takeaways here?
Okay, so the main takeaway is that verification is super important when it comes to scaling test time compute for AI models. Just increasing compute, yeah, it might lead to better performance sometimes. But what these authors show is that by using verification techniques, specifically ones that use reinforcement learning with a verifier, you get much better results compared to methods without verification. And this is particularly important when you're dealing with something called heterogeneity, which is this idea that AI models often find multiple different solutions to a problem that are all correct. The paper dives into the reasons for this, exploring concepts like anti-concentration and showing how verification helps to guide the AI to the best solutions amidst all this heterogeneity. Their experiments, both in a very controlled setting and using real-world math problems, consistently show that verification is key to unlocking the potential of scaled test time compute. And this has some pretty big implications for the way we approach AI development, especially in areas where data is limited.
Thanks for that really great summary. Now back to our regular scheduled programming. The paper talks a lot about two main approaches to scaling this test time compute. They call them Verifier-Free, VF, and Verifier-Based, VB. Can you kind of paint a picture for us of how those two approaches actually differ?
All right, so let's imagine we're training like a junior programmer. In the VF world, it's kind of like you're giving them a ton of perfectly written code, right? And you're saying, study this, figure out the patterns, try to replicate it. And you're hoping they'll kind of learn by osmosis, by absorbing this expert's style.
Sort of like learning by example without any explicit feedback or guidance.
Exactly. Now, VB is more like you give that programmer a bunch of tests and you say, here's the goal, here are the constraints, figure out how to pass these tests, and I'll give you feedback along the way. It's much more interactive, much more iterative.
So VB is more about learning through trial and error, right? And the verifier is kind of acting as that automated mentor in a way.
Precisely. And what the paper argues, and actually demonstrates through a bunch of experiments, is that this VB approach, especially when you're using RL to train the model with a verifier, it's much more effective at scaling that test time compute. And they achieve much better performance than those VF methods.
Wow, okay, that's a pretty bold claim. So I'm sure our viewers are really curious to understand how they actually arrived at that conclusion. What's the core of their argument?
Well, they noticed two really interesting things about how these current pre-trained AI models work. First, they found that these models have a lot of what they call heterogeneity in their solutions.
So even when they get the right answer, they might be arriving at it in wildly different ways.
Exactly. Like you could have 10 different chefs all making the same dish. They might use different ingredients, different techniques, different cooking times, but in the end, you get that same delicious meal.
So there's not necessarily a single right way to solve a problem. There's a lot of flexibility in how the AI approaches things.
Exactly. And what the authors found is that this heterogeneity actually makes it harder for VF methods to figure out the best path to a solution. They're overwhelmed by the sheer number of possibilities. It's like there's too much noise, making it hard to extract that clear signal or pattern from these expert demonstrations.
It's like trying to learn to paint from like 10 different artists, all brilliant, all unique, each with their own methods and styles. It's really hard to distill a single right approach from all of that variation.
That's a great analogy. And then the second thing they found, which they call anti-concentration, is that even though good solutions might be diverse, they tend to kind of cluster together in terms of how efficiently they use compute.
So all the fastest routes from point A to point B, even though they might look different on a map, are roughly the same length.
Precisely. And this is where the VB methods really shine, because that verifier can act like a compass. It can guide the model towards these clusters of efficient solutions. It's not getting distracted by less efficient paths, even if they eventually lead to a correct answer.
So VB methods are essentially learning to be both accurate and efficient, all thanks to the feedback from that verifier.
Exactly. It's like a student who not only learns how to get the right answers, but also learns how to find the most elegant and most efficient way to get there.
Okay, that all makes sense theoretically, but did they actually test this? Did they actually put this to the test?
Oh, they absolutely did. And the results are really pretty compelling. They designed some clever experiments to actually isolate the effects of heterogeneity and anti-concentration.
Okay, now you've got me hooked. Let's hear about those experiments. What did they find?
They mainly used two types of problems. One was a simplified planted subsequence problem, which they designed specifically to test the impact of this heterogeneity on the VF and VB methods.
Ah, so it's a controlled environment where they could specifically tweak the amount of variation in those solutions.
Exactly. And then they moved on to more complex and more relevant math reasoning problems using a large data set of, well, challenging math questions. And this is where it gets really interesting because it starts to mirror the types of problems we want AI to be able to solve in the real world.
Okay, well, I'm ready to dive into those experiments and see how these VB methods performed in action.
All right, let's do it. Okay, so you mentioned this planted subsequence problem. What exactly is that, and how did they actually use it to test their ideas?
So it's this really clever problem where, like, they basically hide a specific sequence of these tokens within a larger sequence. And the AI's job is to find it. And the cool thing about this setup is that they can control how the sequence is hidden. So they can essentially like dial up or down the amount of heterogeneity in those potential solutions.
So by tweaking that heterogeneity, they could really see how well those VF and VB methods performed, right? When faced with different degrees of variation in the possible answers.
Precisely. And the results, they were exactly in line with their theory. So for the VF method, they used this technique called supervised fine-tuning, or SFT, where they basically trained the model to mimic like an expert policy. Think of it as, trying to learn how to play chess by watching a grandmaster.
So they're feeding the model these perfect examples and hoping it will like absorb that expertise and learn to replicate it.
Exactly. Now, for the VM method, they actually trained a separate verifier model alongside the main model. And this verifier acts like a judge, kind of evaluating how well the main model is doing and providing feedback.
Oh, okay. So it's like having a chess coach, right? Analyzing your moves and telling you where you can improve.
A perfect analogy. And they trained this verifier using reinforcement learning, specifically a method called reinforce, which basically rewards the main model when it produces, good solutions.
Got it. So the main model is learning not only from those examples, but also from the feedback it gets from this verifier. It's a much more interactive and guided learning process.
Precisely. And the results were really clear as they scaled up that test time compute, essentially giving the models more tokens to work with. The VB method just consistently outperformed the VF method.
Wow. So even when they made it harder, right, they cranked up that heterogeneity, made it more difficult for that VF method to find like a clear signal in the expert demonstrations. The VB method, with its feedback loop, was still able to kind of navigate that complexity and find those efficient solutions.
Exactly. And it's not getting bogged down trying to like mimic a single expert's style. It's really learning those underlying principles of what makes a solution good, regardless of how you actually get there.
Fascinating. But we can't forget about those real-world math problems, right? The ones from the math data set. Those feel much more relevant to kind of the challenges we actually want AI to tackle.
Absolutely. Those math experiments, that's where things get really interesting. Because here they're testing these methods on a large data set of, some pretty challenging math questions.
Yeah.
The kind that would make even a seasoned mathematician kind of sweat a little bit.
Oh, wow. Okay. A real test of AI problem-solving prowess. So what did they do differently in these experiments?
So for the VF method, instead of just mimicking, a single expert, they tried to simulate a more realistic process of iterative revision. So they kind of stitched together this sequence of both correct and incorrect solutions, with the correct one, of course, appearing at the end.
Ah, so it's like a mathematician working through a proof. Making mistakes along the way, but ultimately arriving at that correct solution.
Exactly. It's a more nuanced and realistic way to represent, how we as humans actually solve these complex problems. And on the VB side, they use this technique called best of n sampling, which, while simpler than full-blown RL, still incorporates that power of verification.
Okay, best of n sampling. That sounds interesting. How does that actually work?
So essentially, they have the model generate multiple solutions and then use a verifier to select the best one. Imagine a panel of judges evaluating different answers and then picking the winner based on certain criteria.
Oh, interesting. So it's like a competition where the verifier is that ultimate judge, selecting the most efficient and most accurate solution.
Exactly. And what's remarkable is that even this relatively simple VB method significantly outperformed the VF method on these complex math problems. They even compared it to a state-of-the-art model called S1, which was trained using a very sophisticated VF approach on this massive data set.
So they're pitting their VB David against a VF Goliath.
You could say that.
Yeah.
And the results were, pretty surprising. Even with limited compute, their VB method, with its focus on verification, actually outperformed this massive, expertly trained VF model.
That's pretty impressive. It seems like, regardless of the task or the complexity, having that feedback loop, that ability to guide the model towards those efficient solutions, really does make a world of difference.
It really does. And it has these really profound implications for, I think, how we think about scaling AI in general. It suggests that just throwing more data and compute at the problem, it might not actually be the most effective approach.
Right. It's not just about brute force. It's about strategic intelligence.
Exactly. This paper suggests that verification is a really key ingredient in that strategic intelligence, especially as we move towards these more, complex AI systems that need to operate in these data-constrained environments.
All of this is so fascinating, but I'm still curious about why these VB methods are so effective. The paper digs into some theoretical concepts to try and explain this. Can we maybe unpack those a bit?
Absolutely. Let's dive into this intriguing world of heterogeneity and anti-concentration.
Okay, so heterogeneity and anti-concentration. What do they really mean, and how do they kind of explain the success of these VB methods?
Well, I've already talked about heterogeneity, right? This whole idea that there are many different but totally valid ways for an AI to solve a problem. Kind of like navigating a city, right? There are tons of different routes to get from point A to point B. Each one might have its own advantages and disadvantages.
Right. Some routes are faster, some are more scenic, but ultimately they all get you to the same place.
Exactly. And the paper's argument is that this heterogeneity, it actually creates a challenge for VF methods because they're trying to learn by mimicking this single expert policy.
So if there are a bunch of different ways to be an expert, it's hard for the VF method to know which one to follow.
Yeah, exactly. It's like, imagine trying to learn to paint by watching 10 different artists, right? You might pick up some cool techniques here and there, but you're probably not going to develop a cohesive style of your own.
Right. But VB methods seem to handle this heterogeneity pretty well. How do they do that?
The key is the verifier. It's not really concerned with how the AI gets to a solution, just whether or not that solution is correct and efficient. It's kind of like a GPS navigation system. It doesn't care if you take the highway or the back roads, as long as you get to your destination, quickly and safely.
So the verifier acts as a filter, kind of sorting through all these different solutions and picking the ones that meet its criteria.
Exactly. And this lets the VB methods really learn those underlying principles of good solutions, without getting too caught up in the specifics of any particular expert's approach.
Makes sense. Okay, now what about anti-concentration? Where does that fit into all of this?
Well, anti-concentration refers to this observation that even though good solutions might be diverse, they kind of tend to group together in terms of their efficiency. It's like saying that all the fastest routes from point A to point B are about the same length.
So even though there might be lots of different ways to correctly solve a problem, the most efficient ones kind of share some common characteristics.
Precisely. And this is incredibly useful for VB methods, because the verifier can very quickly spot those efficient solutions, even when there's all this heterogeneity.
Got it. So the verifier isn't just looking for any correct solution, it's specifically targeting the most efficient ones.
Exactly. And this focus on efficiency is a big part of why VB methods scale so well with with increased test time compute. As you give that AI more time to think, the verifier can guide it towards increasingly efficient solutions within those clusters.
It's almost like having a really, really smart travel agent. They can just quickly find you the best flight deals, even when there are thousands of options to choose from.
That's a great analogy. And this whole combination of heterogeneity and anti-concentration, it really highlights the power of these VB methods. They can use the diversity of solutions to explore, a wide range of possibilities. But at the same time, they're honing in on the most efficient approaches.
This has been a really, truly insightful conversation about this paper. So as we wrap up, what are the big takeaways for our viewers, especially for those who are working on, the cutting edge of AI development?
I think this paper really forces us to kind of step back and rethink how we approach scaling AI in general. Just throwing more data and more compute at the problem, that might not actually be enough anymore. We have to get smarter about how we use that compute. And verification seems to be like a crucial ingredient in that strategy.
So it's not just about brute force, it's about intelligent guidance.
Exactly. By building verification into our AI training and development processes, we can empower our models to not just find the right solutions, but to actually discover the most efficient and elegant paths to those solutions.
It's almost like we're giving our AI systems a compass and a map to kind of help them navigate through this vast, complex landscape of all the possible solutions.
It's a fantastic way to put it. This research really underscores how important it is to move beyond just brute force scaling and really embrace a more nuanced, more strategic approach to AI development, an approach that really puts verification and efficiency as the key drivers of progress.
This has been an absolutely fascinating deep dive. Thank you so much for, sharing your insights with us today.
It's been my pleasure. And for all of our viewers out there, I really encourage you to check out this paper and explore all the possibilities of scaling AI with verification. The future of AI really depends on our ability to make our models not just bigger, but make them think smarter and more efficiently.
Yeah, absolutely.
And with that, we'll wrap up this episode of AI Paper Podcasts. Make sure to subscribe for more deep dives into the latest and greatest AI research. Until next time.